Welcome back. Hope you are enjoying with sinusoidal oscillations, and it is interesting, one of the interesting topics and applications of your op-amp. We are using op-amp as an amplifier, whether it is inverting amplifier or non-inverting amplifier. We are using op-amp and developing the beta network, different types of beta networks, that combining open loop amplifier with beta network, then that is what is going to give you oscillations. That is what we are looking into, and then we are trying to get the best oscillator. Therefore we are going by one and then trying to understand frequency range and frequency stability. Therefore the oscillator which is what is giving you both, that is what is our best final oscillator. That is what people use practically. Okay, what is the technical name of that oscillator, I'll explain later. Okay, now as I told you, did you substitute Z1 and Z2 in beta, and did you find what is beta? If you are done, fine, else let's see. Therefore what is Z2? Z2 is already known to you. Therefore Z2 is nothing but R divided by 1 plus SCR divided by Z1, 1 plus SCR divided by SC plus Z2, again same thing, R divided by 1 plus SCR. I think now SC 1 plus SCR, if you take common, 1 plus SCR will be cancelled. Then what is beta? Then beta is equal to, right, SCR will be cancelled, then this SC will go to the numerator. You will get SCR divided by, then if you take LCM, right, 1 plus SCR whole square, 1 plus SCR whole square plus SCR. Therefore you will get SCR. This is what is your beta. Let's substitute S is equal to J omega. Therefore S is equal to J omega. And what is beta? Therefore beta is equal to J omega RC divided by 1 plus J omega RC whole square plus J omega RC. Right? Then A plus B whole square, which is nothing but J omega RC divided by A square plus B square. What is J square? Minus, therefore omega square R square C square plus 2AB plus 2AB. 2AB means nothing but 2J omega RC. 2J omega RC plus J omega RC. I think you can add. Okay, that we will do in next step. Therefore what is beta? Therefore beta is nothing but J omega RC divided by 1 minus omega square R square C square plus J into 3 omega RC. This is what is our beta. Therefore this is what is our beta. Now we got beta, but it is depending on J. It is depending on J. I want to make it independent of J, then I will get either 0 degrees or 180 degrees phase shift from beta network, right? Therefore what is the condition? To make beta independent of J term, which is imaginary term, right? That is to get 0 degrees R. Therefore that is to get 0 degrees or 180 degrees phase shift. Okay, this is the heading. To get 0 degrees or 180 degrees phase shift. Therefore what is the condition? Can anyone tell? I want to make it independent of J, both numerator and denominator. Then if this is 0, then JJ will be cancelled. Omega RC will be cancelled. You will get 1 by 3. Therefore you are getting directly beta. Therefore what is the condition? Therefore if 1 minus omega square R square C square is equal to 0, right? This is the condition, right? Therefore, that is what is going to give you beta. What is beta? Therefore, what is beta? Beta is nothing but 1 by 3. Your beta is nothing but 1 by 3. Therefore, what do you mean by this? Your angle of beta. What is angle of beta? Are you getting negative sign? No. Therefore, angle of beta is equal to 0 degrees. Your beta network is giving 0 degrees phase shift, and your magnitude mod beta, your gain is nothing but, or loss is nothing but 1 by 3. It is giving 0 degrees phase shift, and loss or the factor is 1 by 3. Right? Write it. Then we will continue. Therefore, from this we are going to get resonant frequency. Therefore, you will get 1 by 2 pi RC. That is what is your resonant frequency. Okay? Take it. Then done. This is done. See how fast we are doing it. Because we know the background. Then we will see the observations part or figure of merit. Then we will go to next oscillator after naming this oscillator. Okay? That's fine. I will give you 30 seconds. Then after that we will see the remaining portion. In the case of RC phase shift oscillator, we got beta network phase shift 180 degrees and 1 by 29 as magnitude. But here 0 degrees phase shift 1 by 3. This itself is saying the loss by beta network is only 1 by 3. But in the case of RC phase shift oscillator, the loss by RC phase shift oscillator is 1 by 29. It is too much. Loss is more. Here the loss is less. Because loss is less, your open loop gain requirement will be lesser. Okay? I hope this is done, right? Now let's use. Therefore, what is the condition? Therefore, to find F naught. Now the first one, to get F naught, resonant frequency. Therefore, what is the condition? Condition is one minus omega square r square c square is equal to 0. At this condition, we got beta network 0 degrees phase shift. Therefore, what is this? Omega square r square c square is equal to 1. Then omega square is equal to 1 by r square c square. Then omega is equal to 1 by rc. Plus or minus 1 by rc will get. Definitely frequency is positive, not negative. Therefore, F naught, the resonant frequency will be equal to 1 by 2 pi r into c. This is what is your resonant frequency. At F is equal to F naught, your beta network is giving what? 0 degrees and 1 by 3. Therefore, at F is equal to F naught at this frequency. What does it mean? At this condition, your beta network is giving 1 by 3. 0 degrees phase shift and 1 by 3. That is the magnitude. Okay. Now, case 2. What is case 2? To get sustained oscillations. Once you get oscillations and resonant frequency, now to get sustained oscillations, your mod A beta should be equal to what? It should be equal to 1. See, because remember your angle of beta is equal to 0 degrees and your angle of A should be also 0 degrees to get total loop phase shift. Is equal to 0 degrees or multiple of 2 pi into n, anything is fine. Now, what is mod A? Therefore, mod A is equal to 1 by mod beta. Therefore, 3. Mod A should be 3. For summary, whatever I told, right? Summary is nothing but what? At F is equal to F naught, right? Your mod beta or beta is equal to 1 by 3 and A is equal to 3. Therefore, your beta network angle of beta is 0 degrees and mod of beta is equal to 1 by 3. Similarly, angle of A is equal to 0 degrees, plus means 0 degrees, okay? And mod of A is equal to 3. This is what your summary. Where F naught is equal to 1 by 2 pi RC. Right? This is the summary. At F is equal to F naught, your beta network is having 0 degrees phase shift. Therefore, overall your A beta is equal to 1. Total loop phase shift and your loop gain both are 1 and positive. Therefore, now tell me what is your open loop gain requirement? Your open loop gain requirement is 3. That is simply 3. Done? Okay. Now, figure of merit. Or what it may be, we want open loop gain, right? What is our open loop gain? A. Open loop amplifier. Let's speak about open loop amplifier. Open loop amplifier. What is open loop amplifier? A. Okay. Therefore, what do you need? We need A to be equal to 3. We can get it. Therefore, we can get it. We need A is equal to 3, and we can get using non-inverting amplifier, because we want phase shift 0. Non-inverting amplifier. Therefore, what is non-inverting amplifier? Minus, plus. We solved multiple problems, right? And this is what is our, let us say, Vi. Then this is what is our R1, then R2. Therefore, tell me what is A, your open loop amplifier. A gain is equal to V0 by Vi. What is that? 1 plus R2 divided by R1. This is what is your open loop gain, right? Therefore, to get 3, right? To get open loop gain 3, let R2 is equal to 2 kilo ohm and R1 is equal to 1 kilo ohm. Therefore, tell me R2 2K, R1 1K, 2K by 1K, 2, 1 plus 2, A. Therefore, your A is equal to 3. That is easy, right? Therefore, if you take non-inverting amplifier using Opamp, we can get gain of 3. That is straightforward. Okay. Therefore, this is what your open loop amplifier. Now, combine open loop amplifier with what? If you combine open loop amplifier with beta network, then that is what your final circuit. Therefore, your complete circuit, complete real circuit if you take open loop amplifier. Therefore, what is your open loop amplifier? Your open loop amplifier is nothing but minus, plus, right? Now this is ground, this is R1, R2. Now output of that is going to series RC, parallel RC. And this output is going to input of your amplifier. Therefore, this is RC, RC, right? Therefore, this is nothing but your beta network. This is your beta network, and this is what is your open loop amplifier. Right? Therefore, this is your open loop amplifier A, and this is your beta network. And listen, it's not a done. Can I write the same circuit in a different way? Is space sufficient there? Yes, there. Let's see. Can I write the same circuit? Can I draw the same circuit like this? Everybody understood, right? Simple. The open loop amplifier is replaced with your non-inverting amplifier, because my gain requirement is 3, then and 0 degrees phase shift, I can go for non-inverting amplifier. And the beta network is already there from starting. Therefore, that is what both are applied. Now, can I write the same circuit like this? Just listen. Now, series RC, parallel RC, right? Therefore, if you see here, can I write like this? This is series RC, right? And then parallel RC. This is resistor and then capacitor, and then this is what is connected to, let us say, ground. Therefore, this is R, C, R, C. Okay? Series RC, parallel RC. Then R1 and R2. That R2 is from series RC combination. Therefore, that R2 is something like this. And your R1 is nothing but to ground. This is ground. Therefore, this is R1 and then R2. Right? And now this is what is the, right, if you take your op-amp, this is your op-amp, the op-amp output is this. Now, the series intersection of series RC, parallel RC. Series intersection of series RC, parallel RC is nothing but your plus. Series intersection of R1, R2 is minus. Therefore, can I write like this? Right? This is a kind of bridge, right? Kind of bridge. Op-amp is in between and R1, R2, RC, parallel RC and then ground. Therefore, you can write the same circuit like this also. Therefore, but if I give you the circuit like this, will you understand? Because we know what is Barkhousен criteria and we know what is total loop phase shift. You know what is beta network. You know what is open loop amplifier. And we combine, we are writing here and there, but looks like it is a bridge, 4 branches, and in between op-amp. Therefore, it is Wien bridge oscillator. What is the name of the circuit? Therefore, this is what is Wien bridge oscillator, which I did not give you before. This is Wien bridge oscillator. Okay, take it. Therefore, this is what is your final circuit. Even in the examination, if this is what is given, just identify series RC, parallel RC. Wherever you have series RC, parallel RC, you can think of about Wien bridge oscillation. Now, number 1, if you ask me frequency range of Wien bridge oscillator, the frequency range of Wien bridge oscillator, right, is in the order of 100 MHz or 10 MHz, tens of megahertz basically. I am taking with respect to olden, right? We can have higher frequency range of oscillations. Reason, right? Now, if you take, right, why it is more? Why the frequency range? The frequency range observation, okay? What is observation? The frequency range of RC phase shift oscillator, right, is less than the frequency range, or I can say, because we are comparing Wien bridge, this is Wien bridge, this is Wien bridge, right, is greater than frequency range of RC phase shift oscillator. What is the reason? What is the reason? Reason is, right, tell me, if you take Wien bridge oscillator, right, reason. Reason, what is your open loop gain requirement here? In the case of Wien bridge, open loop gain requirement is 3. In the case of RC phase shift oscillator, the open loop gain requirement is 29. Okay, then if you ask me, right, if I combine the bandwidth, gain into bandwidth, this is the frequency. If you take, right, this is what is 29, your mod A, this is mod A, that is 29, but the bandwidth it is associated 100 kHz, let us say. But now the gain 3, if gain requirement is decreased, let us say this is what is my gain. Now your bandwidth will increase. Let us say this is what is 10 MHz. This is the bandwidth. But now, right, but here, and this is what is gain requirement, and this is what is 3. But here, this is in the order of tens of kHz. Okay, or I can say this is, let us say 100 kHz. I'm just saying approximately, okay? These are all approximate numbers. Therefore, your gain is decreasing, your bandwidth is increasing. If you take same op-amp, then you'll get at least 10 times, because 29 to 3, your gain is decreased by 10 times, then your bandwidth will increase by 10 times. Okay? But as time progresses, the bandwidth, the inherent bandwidth of op-amp also got increased. Therefore, with respect to that, it is in the order of tens of megahertz, I can say. Okay, that is what people used to get from Wien bridge oscillator. Why gain is 3? Why gain requirement is 3? Because loss by beta network is less. Why? Less number of resistors. Therefore, lesser loss. Maybe now you can say the motivation for the third circuit. Try to implement beta network without resistor. Right? Try to implement beta network without resistor. If you can implement a beta network without resistor, the loss by beta network will be minimum. If the loss by beta network is minimum, then what can you say? Then the gain requirement from your open loop amplifier will be minimum. Then you will get maximum bandwidth. Whatever bandwidth you can get from your amplifier, we can get it. Therefore, highest frequency range of oscillations provided the minimum lowest loss by beta network. That is what is the motivation. Then that is what people went to next circuit, third circuit, where people took beta network, which is the beta network which is not having any passive resistor, explicit or external resistor. Therefore, the loss by beta network can be minimized to get oscillations, and it should satisfy resistors. Not only decreasing the resistor, means you can say without resistor. Without resistors, how will you get phase shift? Therefore, people incorporated some other component. Therefore, if you incorporate some other component without disturbing the loop phase shift, which is 0 degrees, and which is nothing but satisfying Barkhausen criteria, and having 0 resistors, then that will give you best, I can say, best frequency range of oscillations. Okay, that is what we are going to see. Maybe I can say case 3. But before going to third oscillator, the second one, still there is no frequency stability. No frequency stability. Why there is no frequency stability? Because since F naught is equal to 1 by 2 pi RC. If temperature changes, surely your R will change, then your F0 decreases. Therefore, your F0 is not constant. Therefore, F0 is not stable. Instead of saying constant, it is not stable. It will change. Therefore, there is no frequency stability. That is what it is. Okay? Done. Therefore, one is improved with respect to RC phase shift oscillator. The frequency range is improved, but not stability. Okay? If this is over, write down third circuit. I will name the third circuit after completing, something like Wien bridge oscillator. Let me get some water. Hope this is done. Okay. Now write down third circuit. Again, I will name the circuit later. And here also, maybe one more point. Here also, I am neglecting the output impedance of Opamp. Why I am neglecting output impedance of Opamp? Here also, the resistor will be in the order of kilo ohm. If resistor is in the order of kilo ohm, I can neglect the output impedance, because with respect to kilo ohm, you can include the output impedance along with this resistor actually. Strictly speaking, that is also included here, but that can be neglected, because if it is in the order of 5 ohm, 6 ohm, 7 ohm or less than 10 ohm, we can ignore with respect to 1 kilo ohm. But now, if you consider beta network where there is no resistor, then the output impedance of your op-amp will come into picture, because now beta network doesn't have any resistance. Then whatever resistance you have from your open loop amplifier, that will create, that we need to consider. Therefore, that is the reason why maybe for third circuit where, assuming that beta network is not having any resistor, then your open loop op-amp or your op-amp is having some output impedance. That is what we need to consider. Not only op-amp, some amplifier having output impedance, right? If that is what is having output impedance, even though it is a voltage amplifier, right? It is not having zero resistance. Definitely will have 1 ohm, 2 ohm, 3 ohm or less than 10 ohm. That is what is going to create, or that is what is going to be considered, and then we need to analyze the circuits. Okay? That is what I am going to do in third circuit. Because your beta network is not going to have any resistor, which we will not put, because we want to decrease the loss by beta network. Then we want to have more bandwidth from your open loop amplifier. Therefore, you will have more range of oscillations. That is what is the motivation. Okay? I will not name again. After seeing, I will name it. Okay? This is what is third one, but I will name it. I will come back. Okay? Now, again, let us consider this is what your op-amp or amplifier, anything. Right? This is what your open loop amplifier A. And now, this is what your beta network, where, let us say, instead of saying what is it and all, it is generic. This is Z1 and this is Z2 and this is Z3. This is what is taken, considered. You take it as like, and output of this is given to, this is what is sampled from here and then given to your amplifier. Therefore, this is what your beta network. But I am sure Z1, Z2, Z3, they are not resistors. They should not be resistors. Then only you will get the loss by beta network minimum. Right? That is what I want to calculate. Therefore, can I say this is what your beta network? This is what is your beta network. Okay? This is your beta network. But now, I am not going to, whatever we did till now, something like this. We considered what is beta network, then we found what is beta, then we found we want to make beta in term, irrespective of J term, means independent of J term, we made a condition, we got resonant frequency, we got beta phase shift, we got beta gain, then corresponding phase shift by open loop amplifier, corresponding gain requirement by open loop amplifier. This is what we did. But now I am going to combine. I am not going to take them separately, because if you take op-amp, yes, the loading effect is not there to op-amp. Why there is no loading effect to op-amp? The load whatever you are connecting, let us say 1K, but the source resistance of your op-amp or internal resistance of your op-amp or output resistance of your op-amp, if that is in the order of tens of ohm, with respect to 1K, the tens of ohm, the drop internal drop across the 10 ohm can be, or R0 can be neglected. But now I cannot neglect. Therefore, I need to consider the loop, closed loop, which is A into beta. I am going to consider always A into beta, or I need to calculate effective gain. After calculating beta, we need to calculate effective gain of your open loop amplifier, including load. Right? What are baby? Now, if you ask me what is beta, beta is nothing but what? Whatever you are feeding to your amplifier and then whatever you sampled, that is nothing but your beta network, right? Beta network is straightforward. But now, I want to calculate what is my effective gain including load. Okay? What I'm asking is, this is exactly the same. I already explained. Therefore, because it has loading effect. Now, if I say, let us say, right, what I mean is loading effect. Okay? I'm explaining loading. Just listen. If you understand this, you will understand what I'm doing or why I'm going to do effective gain calculation. Even though this is what is A without load. If you have load, this is not A. That is what I want to say. Therefore, that is nothing but loading effect. Even though that is Opamp, but that is practical Opamp. Practical Opamp will have output resistance. Earlier, we used to neglect that output resistance because that is very small. Because the load was in the order of 1K and all. But now load is not there. Resistance is not there. Then whatever R0, that we need to consider. Okay. Now let's see. What is loading effect? I'm explaining. Let us say this is what is my amplifier. This is what is my amplifier. Let us say this is what is A into Vi. Right. Then this is what is your R0. It is a voltage source, right? This is what your amplifier. What is Vi? Whatever input voltage you are giving here, this is what your Vi. This is what your Vi, open terminal. Okay, input terminal is infinity. Therefore, this is what your Vi. Then this is what your Opamp. This is what your Opamp. Okay. Now tell me, if there is no load, right? No, under no load condition. Therefore, under no load condition. Let us say this is what is my V0. Under no load condition. Right? Tell me what is V0. Because if there is no load, right, our load is very high. Let us say, right? Then in that case, we can neglect the drop across R0. That is what I told, right? Therefore, under no load condition, R, whatever load you are connecting, let us say RL, if that is very much greater than R0, or I can say, okay, that's fine. That load RL is very much greater than R0. Because whatever load you connect, if that is very much greater than R0, let us say 1 kilo ohm, this is 10 ohm. Then we can neglect the drop across the 10 ohm. We can say A into Vi will be coming to your load. Therefore, even if there is no load, or which is open case, or the load which is there, which is very much greater than R0. Then tell me what is your V0? Then your V0 will be what? Therefore, your V0 will be equal to A into Vi. Right? Therefore, what is your gain? Gain is nothing but A only. Therefore, what is your gain? Effective gain. Your gain is nothing but A. There is no change. Whatever gain A is represented, that is what is there. But now, under load condition, where RL is not very much greater than R0. This is what is case 1. Right? Now, case 2. With load. With comparable load. Okay. This is no load. Almost no load condition. Okay. Now with comparable load, then this is what is your Vi. This is what is your Vi, and this is what is your A into Vi. Okay. Now this is your R0. Therefore, this is what your amplifier. Okay. Now, this is what is your amplifier. Now, let us say load is connected. Let me say this is ZL or RL. Anything is fine. Okay. Because I am not going to get resistance, I am going to connect some not resistance. That's why I am considering this. Therefore, now if you ask me V0, right? Therefore, now tell me what is V0, right? Therefore, ZL or RL, maybe no confusion. There I will consider ZL. Here you can consider RL. Therefore, now tell me what is your V0. Your V0 is not A into Vi. Are we going to get, right? Comparable load is nothing but what? Both are comparable. Your RL is comparable to your R0. If RL is comparable to R0, then can you say V0 is equal to A into Vi? No. Therefore, now what is your V0? Now V0 is equal to, tell me, RL divided by RL plus R0 into A into Vi. Therefore, can I say this is nothing but your effective load, effective gain. Therefore, this is nothing but, I can say, effective gain A star into Vi. Can I write this as A star into Vi? Therefore, your effective gain including load, which is nothing but A star, is equal to what? RL divided by RL plus R0 into the open loop gain without load, the gain with no load. Okay, therefore this is nothing but your gain with no load gain. This is what is your effective gain. This is very important, which we need to consider. Therefore, but this is true, this is what is called loading effect, right? Your load is going to affect your overall gain, but provided that load is comparable to your R0. If load is comparable to your R0, that is what we need to do. Remember, to do not have loading effect, I told that this is nothing but voltage amplifier. But if you take R0 in the order of 10 ohm, that can be neglected with respect to the load of real load, loudspeaker load, real load like 1K, 2K and all. But now, there is, in the case of oscillators, now the load is not having any resistance, therefore minimum resistance, therefore we need to consider the op-amp internal resistance also. Okay, that is what I am going to consider, and this is what your open loop gain without no load RL. Load is not affecting your gain, but now the beta network, RC phase shift oscillator, Wien bridge oscillator, where the loading effect is not there because the load is very high. That is what is case 1. No load condition or RL is very much greater than R0. But now it is comparable to R0, then we cannot consider simply A into beta. We have to consider A star into beta. Therefore, what is that A star? Effective gain. That effective gain we need to calculate. Okay. First of all, take it. If you understand this, just using that and then calculating effective gain of your amplifier is straightforward. Okay. Take it. Take that. Now time is over for this session. Okay. I'll stop now. I will continue in the next session. Okay. Maybe in the meantime, whatever time we have 2 more minutes or 1.5 minutes for this session. Then you can take it. Then we will continue. I'll apply exactly the same thing to your amplifier and calculate effective gain. Okay. Please continue. Okay. Thank you.